Today's video refers to what are called bond energies. And this is one of the things that very many times is misunderstood in chemistry. So I want to make sure, or not just chemistry, really in lots of sciences. Okay, and the whole idea behind bond energies, or bond enthalpies, sometimes they call them, is the idea of any time you break a bond, it requires energy. It is an endothermic process. Anytime you form new bonds, it is again always an exothermic process. Okay, in biology, a lot of times they say that a little bit differently, but I want to make sure you understand that that is absolutely the key here, is that anytime you break a bond, that bond breaking is going to require energy. It's an endothermic process. I get into that a little bit more detail down here. Let's go ahead and jump to that here. Okay, in order to break a bond, energy is absorbed. That is an endothermic process. It's a positive delta H. Anytime you form a bond, energy is released, which is an exothermic process, and that's a negative delta H. Okay, recently one of the candidates for, she actually won the Miss America pageant, won this contest, and this was her science, whatever you call it. If you go there, let me see if I can highlight that. Anyway, looks like I'm not going to be able to here in OneNote. So, in that video, towards the end of it, she says something referring to the energy is released when the bonds are broken. Okay, and that's where she's incorrect. Okay, energy is not released when bonds are broken. Again, anytime you break a bond, it takes energy to do that. It's actually a really cool video. If you can, I don't know, type it in or however you guys would do that on the YouTube. But she does say at one point something to the effect of energy is released when the bonds are broken. And nope, that is not correct. Okay, and that's what this whole next section is basically referring to, is that, again, it takes energy to break bonds, and it releases energy when new bonds are formed. Okay, now when you do that, you have, a lot of times you're going to see drawings like these, okay? Now, a drawing like this, there's lots of stuff you can get from this. There's no real specific name for this, like a Maxwell-Boltzmann diagram or something like that, okay? This is just a potential energy diagram, okay? And basically over here on this side, they call it potential energy, but basically on this side, you can think of it as the bond strength. Okay, and up on the x-axis, the internuclear distance, you can think of that as the bond length. Okay, and basically every atom gets close enough where the electrons of one atom are attracted to the protons of the other atom, and vice versa. Okay, but not so close that the electrons repel each other and the protons repel each other. Okay, you find a spot where that internuclear distance, or the bond length, and the bond strength are in the most energy efficient spot. Okay, now the bond length, a lot of things can affect that. Of course, a single bond is longer, a double bond and then a triple bond is going to be shorter. Okay, in terms of, what if you have, for example, like F, and II? Well, an iodine atom is much bigger than a fluorine atom is. So the bond length here would be much longer than the bond length here. Again, these are all just about bond lengths. Okay? So, again, triple bonds typically shorter than double, which are shorter than single bonds. The bigger the atom is, the greater that bond length is. Remember, the bond length really isn't the length of the bond, it's the distance between the two nuclei. So, in II, in I2, of course, you're going to have much more distance between the two nuclei than you would in F2, because F2 is a smaller, fluorine is a smaller atom than iodine is. Okay, and then in terms of bond strength, again, same thing. Single bond, weak, okay, which means it's not going to come down as far. The farther down it goes, the stronger that bond length is. Okay? Whereas here the triple bond is going to be much, much stronger. Okay? And then also, as you go down the periodic table, okay, the bonds get weaker. And again, that has to do more distance between the two nuclei, etc. So, those are just some things to think about. Let's look at some examples of this. Again, basically a lot of this stuff that you talk about here, as I just mentioned above. So, here's one example. Example 1 says, while investigating the properties of diatomic molecules, a student finds the diagram below, nitrogen versus nitrogen versus fluorine. And then the student draws fluorine. Okay, so what did the student draw wrong with fluorine? Explain the error with the student's sketch for F2. Now, in terms of, again, this is the bond length. This is the bond strength. In terms of the strength, nitrogen has a triple bond. Okay, yes, you would expect that to be way, way down here. And fluorine only has a single bond, so you would expect it to be absolutely much higher on there. So in terms of bond length or bond strength, that one would be acceptable. Okay, but in terms of bond length, again, a single bond is longer than a triple bond is. Fluorine and nitrogen are in the same period on the periodic table. Yes, a fluorine atom is slightly smaller than a nitrogen atom is, but when you're in the same period, the double, single, triple bond has a much, much bigger impact. So the error with the student's sketch is that the F2 curve should be farther to the right than N2 because single bonds are longer than triple bonds. Okay? So basically this curve can go down the same length, but it should be something more like this. And again, that's a terrible drawing, but something more like that. That doesn't go as nearly far as down as nitrogen does, but because it's a single bond versus a triple bond, the length between them is going to be much, much greater. What if, let's change it up here a little bit. What if we had, for example, fluorine versus, instead of N2, what if we had I2? So again, single bond, okay? So in terms of bond length, F2 versus I2, in terms of bond length, which one's going to be length? Which one's going to be farther to the right or farther left? Again, iodine is a much larger atom than fluorine is, so iodine would be farther to the right in terms of bond length. Okay, and then in terms of bond strength, holy cow, I'm struggling today. In terms of bond strength, okay, because fluorine is higher up on the periodic table, it's as you go down the periodic table, I think I said that right here. As you go down the periodic table, if it's single bond and single bond, those bonds get weaker. Okay, so therefore F2 would be lower. The curve would go lower on fluorine than it would on iodine. Okay? Let's look at another example here. So here we have three unknown elements, X2, Y2, and Z2. We can see that one of them, its internuclear distance is much, much smaller than the other two. And then the other two, their internuclear distances are pretty close, but one of them has a that goes a lot farther down than the other two. So, potential energy, blah, blah, blah. Basically, which ones could it be? Now, notice that in all four answers, it's hydrogen, nitrogen, and oxygen. So let's get rid of the easy one right away. Which one should be hydrogen? Again, nitrogen and oxygen are very close to each other on the periodic table. So their internuclear distances are going to be pretty darn close to each other, okay? And so I would think that those two would be nitrogen and oxygen. So therefore, the one that has the smallest internuclear distance, X2, has to be hydrogen, okay? And that is correct. So X2 must be hydrogen, which means C and D are out. Okay, now it's just a question of which one's nitrogen and which one is oxygen. Okay, now in terms of internuclear distances, they're pretty darn close to each other. And you might think, well, nitrogen's a triple bond, oxygen's a double bond. How does that affect the distance? It does, but more importantly, because nitrogen is a triple bond and oxygen's only a double bond, then this one that goes super far, much farther down, that one has to be the triple bond one. Okay, and again, you might look at it and go, well, oxygen's farther to the right, so it's oxygen's smaller than nitrogen, but it's a double bond, not a triple bond. The internuclear distance doesn't really tell you whether it's nitrogen or oxygen. Okay, again, over here is the bond strength. That's what tells you whether it's nitrogen or oxygen. So N2 with its triple bond must be this lower one here. So N2 is Y2. So that would have to be this one, and then therefore Z2. So the correct answer is therefore A. Okay, so like we just talked about, when you break a bond such as here, when you break that hydrogen-hydrogen bond in H2 to create two hydrogen atoms, it always requires energy. It takes 436 kilojoules of energy to break a mole of hydrogen atoms. Okay? So, what you can do is you can take the chemical equation and you can look at the chemical equation and you go, what are the bonds that are breaking? What's the energy it takes to break all of those reactant bonds? And then you look at the products and go, okay, what new bonds are forming? And you can put those two together to calculate the enthalpy change for the reaction. So you take the sum, that's what this stands for here, the sum of the bond energy of the reactants minus the sum of the bond energy of the products. Now, the reason that it's minus here is because this part right here, remember the products, that's always an exothermic process. Okay, and this part right here is always an endothermic process. So when this reaction, when you're measuring this reaction, you're looking at the reactants and you're adding up all of the bonds in the reactants. And you're getting how much energy does it take to break all of those bonds. And then you do the same thing on the product side. How much energy is released when these new bonds are formed? And then you put them together and you just have to make sure that you subtract them so that you're taking into account the exothermic nature of that bond energy of the products. Okay? Now, if this part, if the bond energy of the reactants is greater, so if this part here is greater than this, then overall you're going to have a positive delta H. If this part here is greater than this part, then you're going to have a negative delta H. And that's going to be an exothermic process. Okay, so depending on which one's more, okay, you know what the bond energies are. For example, in C3H8 plus O2 making CO2 and H2O, 3, 4, 5. Okay, in that case, this is a very exothermic process. Delta H is a very, very negative number. It's a combustion reaction. So what does that mean? It means that the amount of energy that's released when the new bonds are formed, when those CO2 molecules and H2O molecules are formed, is much, much greater than the amount of energy it takes to break those bonds right there. Okay, in our next video, I'm going to do some examples to show you how you will actually use this equation.